So it's a great pleasure to hear Alberto Del Pia from University of Wisconsin-Madison. Alberto.
Hello, everyone, and many thanks to the organizers for putting together this great workshop. I'm really happy to give a virtual talk today. As I was mentioning a few minutes ago, unfortunately, my kid is sick these days, so he's not at daycare, but here at home with us. So for this reason, I couldn't attend the workshop in these days as much as I originally planned to. So please accept my apologies if you didn't see me at your talk. Also, my internet connection is not the best, so we might have to make some changes throughout the talk. Let me know if anything is not working perfectly. Great. So today I will talk about proximity in concave integer quadratic programming, which is a recent result given by Ming-Chen Ma, who is a PhD student at UW-Madison, and myself. Oh. Wait, sorry. Okay. Now, the relationship between an integer linear programming problem, ILP here, and its standard linear relaxation, LP, plays a crucial role in many theoretical and computational aspects of our field. For example, in cutting planes, perfect formulations, and branch and bound. Proximity results, in particular, study one of the most fundamental questions regarding this relationship. Namely, is it possible to bound the distance between optimal solutions to these two problems? Let me mention that while, of course, we can look at different metrics, in this talk, we will always consider the metric induced by the infinity norm. Here, we have a picture to give the intuition behind proximity results. Here, the vector xt denotes an optimal solution to the discrete problem, ILP, while xc instead denotes an optimal solution to the continuous problem, LP. The goal of proximity results is to bound the distance between xc and xt with a function of the input data, which consists of the constraint matrix A, the objective vector C, and the right-hand side vector B. Now, a classic result by Cook, Gerards, Schrijver, and Tardos provides the upper bound n delta for this distance, where n is the number of variables and delta denotes the maximum of the absolute values of the subdeterminants of the constraint matrix A. Since each problem can have several optimal solutions, the statement of the theorem is divided into two parts. So the first part here says that for each optimal solution to LP, there is an optimal solution to ILP at distance at most n delta, and vice versa. The second part says that for each optimal solution to ILP, there is an optimal solution to LP at distance, again, at most n delta. In particular, note that the distance n delta only depends on the constraint matrix A, and is therefore independent on the objective vector C and on the right-hand side vector B. Now, this result has been recently extended to the mixed integer case by Pat, Weismantel, and Weltke, who give the bound p delta, where p is the number of integer variables. Proximity in mixed integer linear programming is actually a quite hot topic at the moment, as several interesting results came out in the past few years. In this talk, however, I want to focus on nonlinear objective functions while leaving unchanged the feasible regions. So now I want to discuss a few proximity results known in the nonlinear setting. And as far as I know, there are not so many. So yeah, please also let me know if you know of any other one. So Granot and Sherinkapov show that the upper bound n delta is still valid if the objective function is a separable and convex quadratic. This result has been further extended to general separable convex objective function by Hochbaum and Shanthikumar and by Werman and Magagnosc. So all these results feature in particular a convex objective function to be minimized. Therefore, a natural question is whether proximity phenomena only occur in the presence of convexity in the objective function. I will now give you an example which seems to indicate that this is indeed the case. In fact, it shows that with the concave objective, the distance between optimal solutions of the discrete and continuous problems cannot be bounded by any function of n and delta. And to construct this example, I will only need dimension 1 and a super simple concave objective, which is just a quadratic polynomial. Any question? Great. So consider this optimization problem for every non-negative integer t. We minimize the function minus x minus 1/4 squared over the feasible region defined by x between minus t and t plus 3/4. And in the discrete problem, we have the constraint that x is integer, while in the continuous problem, we do not. Note that all these problems have dimension n equal to 1, and they have delta equal to 1. In this picture, we can see how our objective function evaluated between minus t and t plus 3/4. Clearly, the unique optimal solution to the continuous problem is xc equal to t plus 3/4. On the other hand, the unique optimal solution to the discrete problem is xt equal to minus t.
Somebody is talking, maybe should close the microphone.
Can you please mute? Venkatesh, please, can you mute?
Great. So, so we saw, right, that
Stefan, can you please mute Venkatesh because we can hear him speak? Or if somebody can make us co-host. Sorry, Alberto.
No problem. Don't worry. Thank you.
பிரச்சனை இல்லை, அது அவர் பேசும்போது தெரியாதா? பேசாம இருந்தாருன்னா பரவாயில்ல. நம்ம சைட்ல சொல்றதுன்னு அவசியம் கிடையாது. நம்ம சொல்லிருந்தா
you can mute this person. Venkatesh is the person speaking. You have the
me?
We're not co-host. Yes, you. Alberto, you're co-host.
Okay, so let me see how to do this. Wait. Do I need?
Or Shmuel, you can do it too.
Oh, here maybe.
Okay.
Done?
I think I was able to do it. Yeah.
Awesome.
Great,
thank you. Thank you. So let me get back. Great. Okay, so yes, this was our example, and you can see here the picture of the example when we see our objective function evaluated between minus t and t plus 3/4, which is the feasible set of the continuous problem. So clearly, the unique optimal solution to the continuous problem is xc, which is t plus 3/4. And the unique optimal solution to the discrete problem is xd equal to minus t. Now you can see that the distance between xc and xd is 2t plus 3/4, and this distance goes to infinity as t approaches infinity. Since in all these problems n and delta are fixed, we have shown that the distance between xc and xd cannot be bounded by any function of n and delta. So this example explains the lack of proximity results in the non-convex setting. However, in this example, a key observation is that the solution x star equal to t, while not optimal to the discrete problem, is almost optimal. Furthermore, its distance from xc is always 3/4. This simple observation leads us to the question that is at the basis of this talk. In the absence of convexity, is it possible to bound the distance between optimal solution to the discrete problem and the approximate solutions to the corresponding continuous problem? And vice versa, is it possible to bound the distance between optimal solutions of the continuous problem and approximate solutions to the corresponding discrete problem? In this talk, we will provide the first answers to these questions. Now, the optimization problem in this example belongs to perhaps the simplest class of non-convex integer programming problems, which is formed by integer quadratic programming problems with the separable concave objective functions. Therefore, in this talk, we focus on this class of optimization problems. For these problems, we answer the questions that we just posed in the affirmative, and so we provide explicit upper bounds. Our bounds are all functions of n, delta, and the parameter epsilon that controls the quality of the approximation. Hence, similarly to the result by Cook, Gerards, Schrijver, and Tardos that we discussed a couple of slides back.
Alberto, are your slides supposed to move? Because we don't see.
No, not yet. Yes,
okay.
no, yeah. Yes, you just have to follow me, but soon I will change it. So, as I was saying, also our bounds will be independent on the objective vector C and on the right-hand side vector B. Finally, we will also discuss how far from optimal are our proximity bounds. Great. So in order to discuss our results, I need to introduce two things: separable concave integer quadratic programming and epsilon approximate solutions. So the discrete problem that we consider from now on is IQP in this slide. So this is the separable concave integer quadratic programming problem where we minimize the sum of minus qi xi square for I that ranges from 1 to k. So this parameter k allows us to control the number of nonlinear variables in the objective, which can be therefore strictly smaller than n. And we also have a linear part of the objective, which is plus h transposed x. The constraints are ax less than or equal to b and x in Zn. By the way, in this formulation, we assume that every qi is strictly positive. Furthermore, we assume that the matrix A is integer, while the remaining data is real. By the way, clearly, IQP subsumes integer linear programming, which can be obtained by setting k equal to 0. On the other hand, the continuous problem that we consider in this talk is QP in this slide. And this is the separable concave quadratic programming problem obtained from IQP by simply dropping the integer constraints. Great. Next, we give the definition of epsilon approximate solution. Now, consider an instance of an optimization problem where the objective function is to be minimized. We assume that this problem has an optimal solution, and we denote it by x opt.
Alberto?
Yes.
Just a quick question. I mean, even the continuous relaxation is intractable, right?
The QP? Yes. You mean from a hard? Yes.
Yeah, right. Because you're minimizing concave, which is usually
yes,
right.
Yes,
okay.
yes, absolutely, yes.
Okay, just checking. Thanks.
Yes, yes. Thank you. Okay, so let's see the definition of epsilon approximate solution. We were saying that x opt is the vector that we assume is the optimal solution. Then, for any epsilon in 0, 1, we say that the point x diamond is an epsilon approximate solution if this inequality holds. So, essentially, this inequality says that the difference in objective between x diamond and the true optimal solution x opt is at most epsilon times the full range of the objective function on the feasible region. Observe that any feasible point is a 1 approximation, according to our definition, and only an optimal solution is a 0 approximation. If the objective function has no upper bound on the feasible region, our definition loses its value because, of course, any feasible point is an epsilon approximation for any positive epsilon. Our definition of approximation is natural for unstructured optimization problem, and it has been used in several other works. In particular, it has a number of useful properties that are, in a sense, needed when we talk about unstructured optimization problems. For example, it is insensitive to translations or dilations of the objective function, and it is preserved under a fine linear transformation of the problem. Great, so we're now ready to finally state our proximity results for separable concave integer quadratic programming. So consider a problem IQP, the corresponding continuous problem QP, and suppose that both problems have an optimal solution. Then again, we break down the statement into two parts. So first, for every optimal solution to QP and every epsilon in 0, 1, there is an epsilon approximate solution X star to IQP at distance at most n delta times 10 delta over epsilon plus 1 to the power of k. Second, for every optimal solution to IQP and every epsilon, there's an epsilon approximate solution to QP at distance, once again, at most n delta times 10 delta over epsilon plus 1 over to the power of k. Recall here that k is the number of variables that appear quadratically in the objective function. And since k, therefore, is upper bounded by n, our theorem implies that for every optimal solution to one of the two problems and every epsilon, there is also an epsilon approximate solution to the other problem at a distance bounded by a function of n, delta, and epsilon. In particular, this distance is independent on the objective function and on the right-hand side vector b, as I mentioned a few slides ago, like in the results by Cook and others. Note that for k equal to 0, wait, this is not, okay, yes, here, yeah, for our, sorry, for our k equal to 0, our problem IQP is an integer linear programming problem, and QP is its standard linear relaxation. And in this setting, our bounds reduce to n delta for every epsilon. Therefore, the proximity bound by Cook and by Cook, Gerards, Schrijver, and Tardos can be obtained as a corollary to this result. Any questions so far? Okay, so before I present the outline of the proof, I want to discuss with you two bad examples which help us understand how tight, or better, far from optimal, are our proximity bounds. In the first bad example, we consider the special polytope P bar defined at the top of this slide. Intuitively, P bar has the shape that you can see in the picture down here. When the parameter t is large, P bar is very long in the x1 direction, which is the horizontal line in the figure, but is very short in all other directions. In particular, the shape forces all the integer vectors in P bar to be on the x1 axis, down here. There are three special vertices in P bar that we will be talking about. One is V, up here. The second is U, here. And finally, minus U, on the opposite side here. Now, V is the vertex of P bar, which has the largest x1 component. U is the integer vector in P bar, which has the largest x1 component. And the vector minus U is just an integral vector in P bar, but it is also the vertex in P bar, which has the smallest x1 component. So you can see that if we consider the infinity norm, then the vectors minus U and V is the pair of, so this is minus U, right, and V, and this is the pair of points which has the largest distance. Our target then is to choose the objective function and the parameter t so that the optimal solution to one of the problem will be located at one of these 2 points, and each epsilon approximate solution to the other problem will be close to the other point. If we manage to do that, then the distance between the epsilon approximate solution and the optimal solution will be very large, since P bar is very long in the x1 direction. Great, so we now discuss the tightness of the first statement in our main theorem. So we consider optimal solutions to the continuous problem QP, and epsilon approximate solutions to the corresponding IQP, and we try to maximize their distance. So here, in this example, we consider the following objective function, f of x over P bar, to be minimized. Intuitively, f is very flat in the x1 direction, but it is very steep in the other directions. This implies that the vertex V up here is the unique optimal solution to QP, the continuous problem. On the other hand, if we choose the parameter t carefully, then we can make a minus u on the other side to be the unique epsilon approximation, the unique epsilon approximate solution to IQP. This implies that the distance between V and minus u will be a quantity in omega of 1 over epsilon plus n delta. And this implies that the distance between optimal solutions to QP and epsilon approximate solutions to IQP can grow linearly, in n delta and 1 over epsilon. This in the case k equal to n, because if you noticed in our objective function, we have that all variables appear quadratically. So it's really just the case k equal to n. In our second example, we discuss instead the tightness of the second statement in our main theorem. So we consider now optimal solutions to IQP, epsilon approximate solutions to the corresponding QP, and we try to maximize their distance. In this example, we consider the same polytope P bar used in the previous example, but we add one new inequality, which is this inequality, this red inequality over here, that chops off points U and V. We're going to call this new polytope P tilde. The main reason we introduce this inequality is so that the vector U is no longer feasible. The objective function that we consider in this example is minus x1 squared to be minimized. Since u is no longer feasible, you can see that minus u will be the unique optimal solution to IQP. And also, with our choice of t written here, we can guarantee that every epsilon approximate solution to the corresponding QP will have the x1 component strictly larger than t. And this implies that the distance between optimal solutions to IQP and epsilon approximate solution to QP can be larger than 2t, which is a quantity in omega of n delta over epsilon. Hence, this distance can grow linearly with respect to n, delta, and 1 over epsilon. In particular, in our second proximity bound in the theorem, the dependence on n is tight and the dependence on epsilon is tight in the case k equal to 1. Because in this example, right in the objective, there's only one component that appears quadratically. Okay, so now that we've seen the bad examples, and we can give the proof outline of our proximity theorem. So we consider an optimal solution XC to IQP here on the right, an optimal solution XD to IQP, and we wish to find an epsilon approximate solution to IQP close to XC and an epsilon approximate solution to QP close to XD. According to the previous discussion, when we saw our bad examples, we know that if XC and XD are close in some components but far in some other components, then this might lead to a bad example. So our main target in the proof is to avoid this possibility. To do so, we use the following strategy. So we iteratively construct a path from XC towards XD. In each iteration, we construct a new point xt in the path. And the special structure of this path enables us to upper bound the distance from xc to xt along this path. Then we investigate the current point xt, and we consider separately three cases. So in the first case, we have that xt and xd are close enough in all components. Since we can bound the distance from xc to xt along the path, then we can say directly that xd and xc are close enough. To conclude, yeah?
You have 5 minutes, Alberto.
Oh yeah, thank you. And this concludes our proof in the first case, because we can just choose the epsilon approximate solution to IQP to be xt and the epsilon approximate solution to the QP to be xc. Now, in the second case, we instead have that xt is far from xt in all the first k components where they do not coincide. If so, then I can guarantee you that we can find an epsilon approximate solution x star to IQP close to xt. Since once again, we can bound the distance from xc to xt along the path, then x star is also close to xc and we are done. And now what about the epsilon approximate solution to the QP? It turns out that we only need to consider the vector from x star to xc and apply it to xt. It can then be shown that the vector that we obtain is an epsilon approximate solution to QP, and this concludes our proof in the second case. Otherwise, if neither of the previous two cases apply, then it means that xt and xt are close in some of the first k components and far in some others. In this third case, we're able to construct the next point in the path and repeat the argument. Specifically, the next point in the path will have one more of the first k components that coincides with the corresponding component of xd. Note that this property of the points in the path is not visualized in our example in the slide because the example is in dimension 2, and if I use this property, everything becomes too simple. In any case, the special property of the points in the path implies that if the previous two cases never apply in the first k iterations, then we end up with a point k plus 1 in the path being equal to xd in the first k components. If this happens, we can show that one of the first two cases must apply in the very last iteration, and we are done. And this concludes the proof outline of our main result. I want to finish this talk just with a couple of open questions related to our proximity results. The first is whether it's possible to close the gap between our upper bounds and our lower bounds, which are currently quite significant. The second question, which I personally find more interesting, is the following. So according to our results, if we have a separable concave quadratic function, then we have proximity results if we consider epsilon approximate solution. But what about a more general IQP where the objective can be indefinite or not separable or both? Currently, we don't know if proximity results can exist for these more general optimization problems. Great, so this is the end of my talk today. Thank you very much for listening, and I'm happy to take a question.